Okay, this is Physics Chapter 8, Lecture 2. There's just 2 lectures in this chapter. On your notes, we're on page 3, and it's called Friction, Work, and Energy. I'll do a solutions video for the Chapter 8 problems all in one video. So the homework that is due tomorrow or on Tuesday, whenever you're watching this, I won't post the solutions until after the second set of homework is due. Okay, so just going through this friction, work, and energy. 4 different forms of energy: mechanical, chemical, electrical, and heat. Energy, mechanical, movement of objects. Chemical, we talked about that in Chemistry Chapter 13, the breaking and forming of chemical bonds. Electrical is motion of charged particles, electrons. And heat energy is temperature transfer. All those forms can be both potential and kinetic energy, except heat, which is always kinetic. So I gave you some, in this table I put some examples of potential energy versus kinetic energy for each type. So mechanical, potential energy would be you would stand on the edge of a cliff, and kinetic would be jump off the cliff, hopefully into water. All right. The chemical, if you just have a molecule, the potential energy is in the bonds, but if that molecule participates in a chemical reaction, bonds break and form, then you have kinetic energy. Is either released as heat or absorbed as heat. Electrical, if you don't have a battery hooked up, then those electrons can't move, and it's all potential energy. We'll have a whole chapter about that. But then once you hook a battery up and those electrons start moving, then you have kinetic energy. And then heat, we don't have any potential energy, and then any kind of transfer of heat implies motion. So the energy equation involving friction. So this is what we're going to use on all of our problems for this lecture, almost all of them. And that is total energy final is equal to the total energy initial, and I'll use F and I from now on, minus the work done by friction. Okay, so let's use this in example 8.6 on page 272. All right, so let me see if I can bring this into view. It says a child shoves his block down a sidewalk. Of course, so there's no height here. If the block starts sliding at 2.5 meters per second, eventually stops, how much work did friction do the entire time the block was sliding? And we have to assume that the sidewalk is level. All right, so let's start with this equation. Total energy final is equal to total energy initial minus the work done by friction. So we're trying to just solve for work done by friction. Now the final energy is 0 because it stops moving and there's no height, right? Stops moving. So if that's the case, you'll have 0 is equal to total energy initial minus the work done by friction. So let's move the work done by friction over to the left side. You'll have the work done by friction is equal to total energy initial. All right, so what is the initial total energy? Well, it is the sum of the potential energy initial plus the initial kinetic energy. But since there's no height, right, it's on the ground, there's not any potential energy. So we have work done by friction is equal to the initial kinetic energy. And that's just going to be 1/2 mass times velocity squared. So work done by friction is equal to 1/2. The mass in this problem is 0.125 kilograms. The velocity is 2.5 meters per second. And don't forget to square that. and you'll have 0.391 joules. So that is not much energy. All right, go ahead and pause the video if you need to. All right, 8.7. So you guys can read along with me. I'm not going to pull the book into view. So it says, friction does 4.5 joules of work on a 430 gram box that slides along a level sidewalk. If the work is done while the box slides 2.5 meters, what is the coefficient of kinetic friction between the box and the sidewalk? Okay, so we know that the work done by friction is equal to force times displacement. So it's going to be friction times displacement. Okay, we know that friction is equal to mu times the normal force. We also know that if it's not at an angle, the normal force is equal to the weight, which is equal to mass times gravity. All right, so ultimately then friction is equal to mu times mass times gravity. So we did that in the last chapter. All right, so work done by friction then would be mu times mass times gravity times the displacement. All right, so this time they gave us the work. So that's 4.5 joules. We want to know mu. The mass is 0.43 kilograms. Gravity 9.8. And then the distance that it traveled is 2.5 meters. So mu is going to be 4.5. I'm going to dispense with the units here. 0.43, 9.8, 2.5. Of course, the units will cancel. It's mu is dimensionless. Okay, and that's 0.43. Okay, so we didn't have to use this equation here because we were given the work done by friction. Okay, and so you'll end up using the concepts in here plus this equation in just a little bit, and we'll kind of put both of those together. So pause the video if you need to. All right, let's look at 8.8. It says, a girl kicks a 155 gram rock down a sidewalk. If the rock starts out with a speed of 3.2 meters a second, how far will it slide down the sidewalk before it stops? Assume the sidewalk is level. And mu sub k is 0.44. Okay, so here we have total energy final is equal to total energy initial minus the work done by friction. Okay, the block comes to a stop, right? So its final energy, it doesn't have any height, it doesn't have any velocity, so that final energy is 0. It doesn't have to be 0. I think there's a homework problem where you have to analyze it while the block is still moving, so it's going to have some energy. But here, in our situation in this problem, it's 0. So we have 0 is equal to total energy initial minus the work done by friction. All right, so we can bring the work done by friction over to the left here. All right, we know that work done by friction from before is friction times displacement, F delta x, and that'd be potential energy initial plus kinetic energy initial, but it's on a level sidewalk, so it has no height. We know that friction from the previous problem is mu times mass times gravity. So friction is mu times mass times gravity times delta x. And for kinetic energy, the equation is 1/2 mv squared. Masses cancel. So I have mu g delta x is equal to 1/2 v squared. All right, we are solving for delta x here. All right, so delta x is equal to 1/2 v squared over ug. All right, now we can plug some numbers in. So our velocity is 3.2. Don't forget to square it. We have a mu of 0.44. And gravity is 9.8. All right, when you plug all that into your calculator, you get 1.19 meters. Okay, gonna erase this. Let's look at 8.9. So it says a 2.3 kilogram wooden block slides across a carpentry shop's floor. If the floor is level and the block stops after 3.5 meters, what's its initial speed? Okay, so we're going to start with total energy final is equal to total energy initial minus the work done by friction. We want to know the initial speed, so we're looking at velocity here. Okay, it's a carpentry shop floor, so and it comes to a stop after 3.5 meters. So we know the final energy is 0. So we have 0 is equal to total energy initial minus the work done by friction. So bringing work done by friction over to the left is equal to total energy initial. All right, so we know that this is going to be friction times delta x. And that is going to be potential energy initial plus kinetic energy initial. Doesn't have any height. Sometimes it does, so you have to read closely. We know that friction is mu mg. All right, that's just the normal force times mu times delta x is equal to 1/2 mv squared. We're solving for v. We have the masses go away. So v, doing the algebra, is going to be the square root since it's squared, and then we would flip and multiply that 1/2. So that'd be 2 mu g delta x. So that's the square root of 2.52. 9.8. Let's dispense with the units for just a second. And then it went 3.5 meters. And that would be 5.97 meters per second. All right, pretty cool. Know the formulas, do the algebra. It's not so bad. All right, gonna erase this and we'll go into the last concept of the chapter. And that is power. So we're at the bottom of page 4, energy and power. The power equation, P is the change in work over the change in time. The unit for power is a joule per second. And you've probably heard of this unit. A joule per second is called a watt. Maybe you've seen a 60-watt light bulb or whatever. You know, you've probably heard of watts before when it comes to electricity, especially electrical devices. All right, so let's finish this chapter up with 8.10 on page 276. So it says the engine in a machine is rated at 125 watts. If this machine uses a force of 55 newtons to move an object 351 meters, how long will it take the machine to complete the task? Okay, so we have power is equal to change in work over change in time. We want to know how long, so we're solving for time. time is equal to the work over power. We know that work is force times distance. Okay, so F delta X over the power. All right, so our change in time, the force is 55 newtons. The distance in the problem is 351 meters. And then how long, and the power is 125 watts. Okay, so that is going to be 154.4 seconds. All right, so the homework for this section, you've already done review questions 1 through 6 and practice problems 1 through 5. So it's to finish that up. Review questions, page 284, 7 through 10. Practice problems, page 285. You can do 6 through 10. All right, the next video you get will be a solutions video for all the review questions and practice problems from chapter 8. And I'll talk to you next time.